thanks, Paul. We'll just get right into it. All right. So last Thursday, you all learned how to do quantum Monte Carlo calculations for molecular systems. So, we are a center for predictive simulation of functional materials. And so, this is a fine time to distinguish molecules and materials. Is that, the ansatz that we use and the general projector Monte Carlo, variational Monte Carlo framework is very similar it's pretty much identical between the two, but there are some very unique problems with doing solid state and material calculations over molecules. So whereas molecules are basically like bounded systems, like they can get very, very big. But it's like we're talking like thousands, tens of thousands of atoms, think of a protein molecule or something. But in principle, it's important to enumerate all the atoms there, and then you have your Hamiltonian, and then you're off to the races. With solids, traditionally the motifs which these things are built out of are, quite a bit simpler than like your average like practical molecular calculation. But the interesting physics comes about because there are a lot of atoms. When we start talking about materials, we're talking about trying to predict the properties of things that are, order microns or larger. If you think of like a grain boundary in like a metal or something, and, order 10 to the 23 atoms. This is orders and orders and orders of magnitude larger than even the largest molecular calculations you would probably think of. And so, when we're dealing with these types of systems, we'll often refer to these as like, what are the properties of this material in the thermodynamic limit? So, basically we say that a micron rounds up to infinity, 10 to the 23 rounds up to infinity. And so, what are the properties of the material in this limit? So that's great, I can say it, but like the problem, and in fact, the entire point of this class is how in the world can you make comments about real materials that are effectively in the thermodynamic limit with only between 10 and 1,000 atoms. So we're going to structure this lecture basically breaking it down. Basically, how do we pose the problem of a macroscopic system in a way that we can computationally deal with? And so we'll spend a little bit of time talking about boundary conditions. And then, I'm assuming you all have some experience with DFT. We'll start talking about the finite size effects in density functional theory, like how you mitigate these. And that will provide a very nice stepping stone for dealing with analogous finite size effects in QMC, but then also some totally new finite size effects. And then that's probably going to be most of the theory heavy stuff. In addition to the dimensionality of these systems, like you might have to run like, thousands of electrons. There are some unique considerations for what kind of wave functions we have to like use. So, we're going to talk about the types of wave functions, how to bring down memory, because some of these systems can get big. And then I'll give you an overview of the lab of how you can apply this both in your workshop exercise and in your future research. So basically, molecular systems work in what's called open boundary conditions. Is that, I write down where all the atoms are. I can write down their interactions, and there's basically a finite boundary for this. So a way you can think about this is if I'm trying to build up a solid, is let's say I have a unit cell over here. Well, then I can just multiply this 2 by 2 by 2. And, we have our little tiny microcrystal over here, and it's surrounded by vacuum. And I can keep going up, so on and so forth, until I run out of steam. And, eventually I'll hopefully have something that will be representative of like a real material. Incidentally, this is how nature works because nothing is infinite. So it's like, your glass of water actually has boundaries on it. So the problem with this, though, is that more often than not, we're interested in bulk properties of the material. So like, we're interested in the conductivity, we're interested in the bulk modulus, we're interested in the equation of state. And you know, in a glass of water, the surface effects are not really that big of a deal for determining those properties. But when you're in these tiny systems, the surface actually makes up a significant fraction of the uh, cell. And there are entire journals devoted to surface physics, and they are completely different from bulk physics. And so this is actually, I mean, trying to reach the thermodynamic limit in this way is like kind of needlessly wasteful, needlessly complicated. And so what we do, like DFT, what we do, what pretty much what field theorists do, what everybody does when you're trying to mimic these infinite systems is instead what I imagine is I have a little unit cell over here, and I'm imagining, so there's a fixed number of atoms in this box, right? Now, I'm not dealing with an infinite number of atoms, but this thing is sitting in an infinite lattice of replicas. And so what happens is that like the way the boundary conditions are set up is if I have a little atom like this that traverses through this little boundary over here, notice there's one from up here that comes right down. And so if you've ever played the old console game, Atari game, Asteroids, that game works in periodic boundary conditions, is that you can never really get out of this box. You can like pop out one side, but you always come back in the other. And so what this does, this basically accomplishes two things. One, we don't have surfaces anymore. So that really simplifies the, you know, as we start building this up to larger and larger systems. The other thing is that if you're in a truly infinite or a, you know, box like this, it's extremely amenable to like Fourier math, and that makes everything significantly simpler. So everything we're going to be talking about is in this picture over here. All right, so finite size effects. What is a finite size effect? So provided you've converged everything else like plane wave cutoffs, you know, like the standard systematics, a finite size effect is any deviation from the infinite system answer from the thermodynamic limit, which, unless you have a very good reason to be thinking otherwise, that's the right answer. And so, you know, examples of this would be things like, you know, if I ask what is the total energy of my crystal per cell per, you know, unit mass, if I ask the pressure, the electron density, like whatever you like, typically if you plot these as a function of increasing cell size, you won't find that these are completely independent. And what you're looking at is basically the finite size effect that you do need to control to within the tolerances that you need for your given problem. So, you know, I might have an equation of state calculation where I need to converge this to a millihartree per atom. I might need like 1/10 of a kilobar or something for this, you know, it's like that's system dependent, but you do need to know what it is and how big it is. And so, you know, we don't really harp on this a lot in DFT because DFT has some really nice properties, but just as kind of like a stepping stone to understand how finite size effects work in a traditional DFT context and how we're going to use them is we really need to start with Bloch's theorem. So I'm going to warn you already, I'm going to do as good of a job as I can to give you the highlights, to give you an intuitive kind of picture for how this works. But like the main way that you need to make this intuitive is to go read Ashcroft and Merman, or go read Richard Martin's electronic structure theory, or spend some time on the Wikipedia page, play with the math yourself, just convince yourself that this is true. But, you know, provided those caveats are there, Bloch's theorem basically says that for electrons in a perfect crystal, there's a basis of wave functions with the following two properties. One, of course, we have energy eigenstates. That's kind of the entire point of solving Schrodinger's equation. But when we're in a perfect crystal, we have things like, well, one of the defining features of a crystal is that it has a space group associated with it. Is that whenever you engage in translations, you know, like by one unit cell, you don't change the crystal by definition. And if I do things like point group operations, you know, if it's in the space group of the crystal, it's going to leave the crystal and actually this potential rigorously invariant. In fact, one of the, you know, another way you can think about this is that if I write down the crystal Hamiltonian is that this Hamiltonian is going to be invariant to any of these space group operations. So provided that that can happen, the second part of Bloch's theorem says that for all those little eigenfunctions, you can rewrite, or you can cluster them or write them as a e to the I k of k times r times a different function. And you're like, well, why go through this work of like factoring like this? And it's because this u is completely periodic in the primitive cell. And so in a weird kind of way, even though we might be dealing with a perfect crystal of like 10,000 atoms, in some sense, because of the crystalline symmetry, is that because these things transform under the space group, it does simplify the solution quite a bit. And so, if I go and rewrite Schrodinger's equation, rather than write down the Schrodinger equation for the whole box, I can actually write it in the primitive cell like this, where it's like all the complicated, phase information I can throw into the kinetic energy operator. And then I have these little eigenfunctions that, once again, are completely periodic in the box. And I can always get back to the original box just by slapping on this phase factor. So, I spent a lot of time belaboring that point. Why do we care? Is that there is a one-to-one mapping between supercell calculations and then this kind of like do it in the small cell, but do it at different K points. And so basically this is, and DFT, this is like a really powerful time-saving device. Because one of the problems here is that, it's like to do this general eigenvalue solve in the raw crystal, it's like this thing is going to have, let's say this is a 2x2. This is going to have 4 times the number of electrons, 4 times the number of orbitals than the primitive cell. And I need to build matrices that are, 4 times 4 times as large. So 16 times the size. I incur an n cubed cost to, do the eigenvalue solves. So that really adds up. But for single particle theories, like bona fide single particle theories like LDA, PBE, where there's no coupling between the K points, is that I can actually solve it in the tiny cell. So one, I get a lot of savings by just working in the cell. But two, I can actually do these K points individually and separately without talking, without having them talk to each other. So that is also extremely powerful. So, in DFT, for example, like even just as a matter of course, we will tend to prefer to work in this. And then if we need to go up to something like this, we always know that we can take the solutions over here and map them onto solutions over there. More on that later when we start talking about QMC. So in DFT, one of the major things about the finite size effects here is that, whenever we do a DFT calculation, one of the standard things we have to control for is we have to do convergence tests for QMCPACK grid or K-point grids. And so what we'll do essentially is we will start considering, using larger and larger grids over here, and then just watch how properties change with respect to it. So here's an example of the total energy in Hartrees for a lithium. I think this is a lithium unit cell taken from one of the exciting tutorials. That's the name of the code, but I guess it's also pretty exciting. And what you'll see is that as you start increasing the grid size, this energy changes a lot, and then it kind of settles down. So one of the things that happens in like DFT is that, we do have one thing is that if you don't use a sufficiently large simulation cell, or if you don't use a sufficiently large K-point grid, your densities are not converged. Like as you start going larger, the self-consistent density that you're dealing with, it does have a limit that you do need to hit first. In fact, we will in the lab, we'll do a self-consistent step before we do the non-self-consistent. But once you've converged the density, there's another source of finite size error, which is basically it's basically an integration error. Is that if I ask for like, what is the energy of my system per unit volume, or per unit cell, these things usually look like integrals over k-space, aka over the Brillouin zone. And so it's pretty straightforward to see that if I have a very, very, very coarse k-grid, I'm going to incur an error in the estimation of this. And so uh, that's kind of like another source where, once we've already controlled for the density, then, we have to increase this to such an extent that we can basically keep the integration error down. So, in effect, the standard procedure that you already do in DFT that they teach you from pretty much your nursery days when you're doing a band structure calculation or doing an equation of state calculation is designed to solve this, is to remove all of these sources of finite size effects. And actually, unless you're doing molecular dynamics, this is sufficient to get rid of the finite size effects in DFT. One final point before we go on into QMC is that I mentioned over here that we do these little like Brillouin zone integrals. And so we do have grids that we set up and we try to do these integrations over these grids. Now, because we are dealing with crystals and because they do obey space group symmetries, there's a pretty nifty little trick we can do. And that is we can exploit the symmetries to cut down the number or to cut down the region of k-space, to cut down the region of the Brillouin zone that we need to consider to give a full description of the material. So, for example, this is a 4x4 Munchausen-Pack grid, but because the space group symmetries for this square lattice and the point group symmetries, if I look at this K point, this is not completely radically different from this one. In fact, this one is rigorously related to this one over here by the space group operations of the square lattice. For instance, if I do a rotation by 90 degrees, I can get over here. And if I do reflections, I can get over here. And one of the things it's going to do is it's not going to change the energies of these eigenfunctions. They're still going to be valid eigenfunctions. So if I do a K-point calculation here, not only is that kind of sufficient in a way, but I can also rigorously get the information from the other guys just by doing this, by doing the space group operations. And so what we do here is we restrict the amount of K-space we consider. So this is a 4x4 grid, that's 16 points, but the only ones that are symmetry equivalent are these three. So that is a pretty significant savings. And then, I showed the example over here from a 5.5x5x5 mesh. This is a 5x5, so that's 25. But you can notice that all I need to do is consider 6. And those are that's where all the physics is. That's where all the unusual stuff is. So we can kind of focus on that and just rest assured that we can go through and build the rest of this thing if we ever need it. So whenever you run DFT calculations with symmetry, you'll notice that if you have symmetry turned on, it'll give you these K points, but there'll usually be weights associated with it. So if I say that this thing has a weight of 4, that means that this is symmetry equivalent to 4 or 3 other K points in the Brillouin zone. So that will be important when we twist average later. But anyways, moving on. So unfortunately, the statement of Bloch's theorem that I gave you is rigorous for single particle basis functions. It's rigorous for single particle Hamiltonians. But when we move to a many-body framework, we kind of lose a lot of the convenient power of Bloch's theorem. But it's still important because, one, we're building up our trial wave function as a Slater determinant of orbitals which individually obey Bloch's theorem. So for construction and analysis of these things, it's still really important to utilize this. But the other thing is that if we get rid of the Jastrow, this thing maps pretty well on, it maps on to basically like a Hartree-Fock wave function, which is actually kind of like a single particle thing, or it's mappable onto a mean field single particle thing. And we know that there are one-body finite size effects present in that. We just talked about all the types that can happen in a single particle theory. So it's still important to deal with these, even though we've kind of broken the rigorous correspondence. And so what we do is we introduce a wave function on SOTS. This is a, you can call this like a twisted wave function, is that whenever you take a particle and move it through the box, return it back to where it started, it will pick up a phase. And that phase specifically is given by this k vector. You notice it looks a lot like the k vectors we were already talking about. This is in QMC parlance, the twist vector. And then what we do is we define twist averaged observables as like so, where we basically take a wave function, it depends on this twist, we measure our observables over it, and then basically what we do is we just do VMC, DMC, and you can basically show that this becomes a k-point integral average of an expectation value of this that depends on a twist. And so, what's the point of doing this is, well, it really mitigates the finite size effects, or sorry, the single particle finite size effects in a unit cell. And the way you can see this is that this is an example of a 2D fermion system. And, I'm using the naive kind of K vectors over here. And in the thermodynamic limit, since this is a Fermi liquid over here, it has a Fermi surface. The properties inside and outside the Fermi surface are pretty different. And in fact, a lot of the interesting physics comes about because this is a nice discontinuous sharp boundary over here. Now, if I just took the plane wave solutions that were consistent with these boundary conditions and occupied the orbitals like this, then what would happen is that some of these guys would be like completely within the boundary. Some of these would be right on the Fermi surface, and you're going to incur a fair amount of I'm not going to say error, but novel physics just by preferentially sampling these points. And so in principle, what you could do is just by moving this off, you can start exploring areas a little bit closer to this, a little bit outside of it, and it really mitigates the statistical weight of these guys over here, which are pretty not representative of a true thermodynamic limit. And so, so this idea over here is called canonical twist averaging. Canonical because we're preserving the number of particles throughout the procedure. I'll go into this more later, but basically any observable that you calculate in the QMC calculation, we are going to twist average these things. And so, this guy over here is an integral. In very standard form, we can basically go and compute integrals discretely by, if these are the grid points, and I can just average this guy over the various grid points. Notice that since I have a statistical weight in here, this allows me to fold in information about the multiplicities I was talking about. So it's if I were doing this over a uniform grid, like here, these weights would all be 1 over the number of K points. But if I decide to reduce it to an irreducible Brillouin zone, then some of these K points would get a lot more weight. And so, yes. So anyways, pretty straightforward. In practice, much like in DFT, I can do these K point calculations independently. Is that, these twisted wave functions don't really talk to each other. So that's pretty nice. I can farm these out. And then something a little unusual, but because QMC is a statistical discipline, we do get a little bit of advantage by farming these twists out. If I need a 1 mil-Hartree per atom error bar on something, what I can do is I can actually, if I'm running 4 twists, I can basically run each twist with twice the error bar on it and still get to kind of where I need to be for the final twist average answer, because these errors combine, or this is a statistical average, and it does depend on the number of samples, and twists are samples. So that's great. So for efficiency's sake, you can actually tune this. And so it's not like you have to do 4 times the amount of work in QMC to do this procedure. There's a little bit of a burn-in time. You don't get the equilibration for each independent K point for free, but the stats you do. And then, of course, how many twists are enough? In general, well, I mean, like, this is kind of like the answer for everything, but it depends. It depends on the size of the system. It depends on whether it's metallic or insulating. But you will almost always know by doing a twist grid convergence plot. So, if you start off with a single twist and start increasing the number of twists, you should see it plateau. And if it hasn't plateaued, then you either need more or there's a bug. So, and then of course, Nexus is like really nice for this. I used to do this by hand. It's not that crazy to do it based on the way the code is set up, but like in terms of like doing these calculations in a primitive cell, doing the twist grid in a supercell using symmetries, it's like that's way better than it was. Out of completeness, we're not going to talk about this in the lecture today, or in the labs or for the rest of this lecture, but I do want you to know about an alternative twist averaging scheme, which is called grand canonical. Grand canonical because what happens is, all right, let's take a look at this guy. I have a K vector right here. So this is a Slater-Jastrow wave function, but one of the things about Slater-Jastrows is you kind of need to figure out how many electrons are in it. For canonical, we just set that equal to the number of electrons in our cell and then just kind of take how it comes. But that does introduce known errors. That error really drops off with as a function of system size. But what you can do is in order to better represent this guy, what you'll do is you'll take a twist and then you will occupy it up until you hit the Fermi surface. So for, this is actually pretty powerful. Like, I mean, one with Fermi surfaces in general, but especially for like weirdly shaped ones. And that's actually more in line with like how nature works on this front, because like, technically speaking, you set the chemical potential that determines the occupation. We set the number of particles because it's easier, but there are advantages to doing it this way. One of the big advantages is this is a measure of the I believe this is a momentum distribution. And this is the canonical twist averaging scheme. This is the grand canonical twist averaging scheme. And you can tell there's a finite resolution here. It's blocky, but there are some spurious features over here. You could imagine that if you just kept cranking it, that this would go away. But for the same amount of work, this guy looks a lot more well-behaved. So generally, it's a good thing to do. Nexus supports doing this pretty easily, but there's a lot of theoretical backend that you kind of need to be aware about. I recommend reading this paper. It's a good one, but just keep it in mind. So, cool. We have talked about DFT finite size effects. We've shown how we can do an analogous procedure in QMC. Are we done? No, not even close. So basically, the twist averaging procedure in QMC mitigates the single particle finite size effects, which we've belabored quite a bit so far. But the entire reason we're doing QMC is that it's a many body theory. And so, shocker, we have many body finite size effects. Now, fortunately, the ones that we have to worry about for energies and pretty much for energetics and stuff like that falls in the category of two body finite size effects. So I can tell you right now that like one of the easiest ways and actually the most surefire ways to do this is to run several different supercells and then see where the energy goes. Analytic results in 3D and plenty of empirical evidence confirms that this two-body finite size effect scales like 1 over the number of atoms or 1 over the system size. And so what I'm doing is I'm showing you an example over here of diamond silicon. And basically, I want you to focus on this PBC plus A. Like this was taken from a finite size correction paper, but this is twist averaging. This is what we were just running you through about why you should do it. And what you see is that for PBCA, it's a little jumpy, but like this thing looks like a line. If you did not do twist averaging, this is what it looks like. That is not super great. So kind of why we do finite twist averaging is so that we can eventually handle these like many body finite size effects. So so then much like the twist averaging procedure, how do I know if I'm converged with regards to the cell size? You just run multiple cells and see if the energy is like, see if it converges. That is the gold standard. That's also the thing that we hate doing the most because, you know, like I said, it's like 32 atoms over here. That's not too bad. 256 atoms, you can do it, but you're probably not doing that on your laptop. So, so we really need kind of ways to like understand where this is coming from and like how do we correct these. And so just taking a step back, like so two-body finite size effects, a fun way to, well, I'm not sure if it's a fun way, but like one way you can wrap your brain around this is that pretend that I'm doing a single unit cell calculation over here in periodic boundary conditions. Let's say that these are electrons. So I can eliminate all the one-body finite size effects with this. And then as I start sampling the many-body wave function, allow these guys to move, you know, I can compute the energy, I can do DMC on it, everything is fine. This is a well-posed problem over here. But what happens is that like, or actually, yeah, this is a well-posed problem. I can compute all the orbitals of Bloch's theorem. I can compute all the electrostatic interactions with something like Ewald or optimized breakup. But let's say that I take the exact same system and just tile it to a 2x2 supercell. And if we start out with like, you know, we go from 2 to 8 electrons, is as I start evolving this configuration in QMC, what's going to happen is that these these electron coordinates are going to respond to what's happening over here, and they're going to respond to what's happening over here and what's happening over here, and basically to what all the other electrons are doing in the box. They're going to basically interact by the Coulomb interaction, and this is like the effect of this is basically electron correlation. Like this is why we do QMC, is to capture this kind of things or capture this kind of thing. And you know, if everything's converged correctly, this won't show up in density. This won't show up in any properties that are single particle and resolvable in the unit cell, but it will show up in two-body correlation functions. And basically, since our Coulomb interaction relies on these guys, you can actually pick up significant energy errors. All right, so how do we fix these? I already talked about it. The gold standard here is to just extrapolate it away. So it's easily validated, but it gets crazy expensive. So the other option you should consider is to see if you can correct it away. And there are several ways of doing this. In fact, I believe that the lab runs with the model periodic Coulomb potential turned on. But we have ways of, you know, I mentioned that like, you know, once things are large enough to be converged, you know, you still kind of have what's essentially an integration error coming from these guys. So there are finite size correction schemes coming from those. And then there's a DFT based one. It's not super great, but it's much better than nothing. So the model periodic Coulomb potential is that basically, you know, it's like the Ewald gets the Hartree term exact, but, you know, the exchange correlation energy is a little messed up. So you can actually estimate, I mean, you basically estimate the correction coming from this error with the model periodic Coulomb. So like I said, this is an estimator, it's turned on. And then, you know, this does get rid of a fair amount of the finite size errors. I should have a figure showing this later. Okay, we'll come back to that. But and then as I said before, you know, QMC has because of many body, we have like two body correlations. And so the actual potential energy in Fourier space is, you know, this is the structure factor over here. That's the potential energy. It depends on this guy. Provided everything's converged, there is an integration error. So what this is showing is electron gas and I'm showing you the structure factor over here. And then what I want you to notice is that, for the smallest cell over here, I have a discrete set of points right over here. And then I go up to a larger system. And then, I have a different set of points. I have more points because it's a finer grid, essentially. 54, I have even more points. But the important thing is that much like the Brillouin zone integration error, this is not really revealing any new information about this S of K object. It's basically changing the sampling of it. And so, at least a big chunk of this error that we're missing is coming from not including the stuff coming from down here, which is actually kind of important because notice there's a 1 over k squared over here. That's pretty large. That's a pretty large weight for this like bit that you're just throwing out. But we do have an SK all estimator in the code, and then we do have a QMC finite size correction tool that is built whenever you build QMCPACK. I wish I could run you through this, but I opted against doing a supercell convergence test because those get really unwieldy on 4 cores. So, and the final thing is that this is the Qui-Jang-Krakauer correction. This is completely DFT based. It's in Quantum Espresso. And the idea here is that, whenever you write down the exchange correlation energy for the electron gas, what people don't talk about is that that has already been extrapolated to the thermodynamic limit. So whenever you're doing a finite DFT calculation, you might be running with 20 electrons, but the exchange correlation energy is the one that corresponds to the infinite system limit. So what Qui-Jang and Krakauer did was they basically kept the size dependence of the homogeneous electron gas exchange correlation energy. So they did not extrapolate it to the thermodynamic limit, basically so that you could see where, if you're running a finite system size, where is your correlation energy and your exchange energy relative to what we would expect in the thermodynamic limit. And so this is actually a fine thing to do. And it's a lot better than nothing. So one of the advantages to this is that it's extremely low effort. Like if you already have espresso, you can just do DFT equals KZK. It gives you the approximate total energy correction. So it does not make the distinction between kinetic energy and potential energy in the same way that the exchange correlation energy does not make a distinction between the kinetic and potential, but that's something to keep in mind. All right, so those are all the big things we have to worry about in terms of finite size effects in, one body and 2 body finite size effects. The rest of this talk is largely going to focus on okay, so, I am trying to run a snapshot of this particular crystal. It's got 100 atoms in it. How do I represent the orbitals? How do I make it so that I don't saturate the memory on my system? And how do I make it so that it's, reasonably fast? So, so at the high level, this is the same ansatz as we would use in a molecule. We typically don't do multi-determinants over here, but yeah, so we have a determinant of single particle orbitals. But molecules use localized basis sets. They use Gaussians, and you can actually use Gaussians, and you can use periodic Gaussians in solid state calculations, and sometimes we do. But the heavy hitter DFT codes that you would use for solid calculations work completely in Fourier space. They are plane wave DFT codes, and there's many technical reasons for this. Like they're systematically convergible. Let me see here. They don't have linear dependence issues in the basis set, but it does come at a cost. The memory requirements are basically increases cubically with systems, basically increases cubically in the linear dimension. So that's not great. The other thing is that let's say that we have so we need to increase the plane wave cutoffs. We need to increase, like, how many basis functions we use to represent our orbitals, usually by going to higher K vectors and stuff. But one of the unfortunate things is that when you start going to heavy elements, you do need to resolve very small length scales to reasonable precision. So if you have, like, a solid calculation where you have a very localized charge density or something, then that is going to increase the calculation significantly over and above all the other problems we're dealing with in terms of, like, dealing with a solid state calculation. So, and then, with molecular calculations, your basis functions are Gaussian, so you can basically just evaluate, like, for every orbital, you can actually do a very short contraction and, like, evaluate the orbital. But if you start doing that in solids, given that the basis set basically scales, like, naively, like the number of plane waves, you run out of steam in, like, very tiny calculations. And so we need to basically move from, like, this, like, plane wave kind of formalism into, like, a more real space-based thing. And that's pretty much what we do. This is one solution. It's a pretty good one, pretty much near optimal in terms of, like, computational cost. Is that what we do is is that whenever we take a plane wave set of orbitals from, like, a code like Quantum Espresso, is we basically put that on a real, or we do a Fourier transform, put the orbital onto a real space grid, and then just we just use B-splines to represent it. This is really nice. It is a compact basis set. And basically it's going to be 64 grid points per orbital, and it does not depend on how big the system size is, how big the basis set size is. You land in a particular part of this box. It's basically a lookup to find out which B-spline coefficients you have to do, or which B-spline coefficients are relevant. You evaluate it, and then you're off to the races. And so this is, in addition to being bounded with system size and basis set size, this is also one of the more performant parts of the code. Like, this is, like, quite a bit of effort has gone into offloading this, to batching it correctly, to making sure it is properly vectorized. So this is about as fast as you're going to get this. Like, unfortunately, the downside of this is kind of like a flops to memory trade-off, is that it's not very intensive to evaluate these types of orbitals, but the cost of this is you have a pretty big spline table. And so it's not unusual for a standard solid state calculation to have, like, a wave function that, once it's in spline form, is like gigabytes. And then you can very easily run out of steam with that. You'd be surprised on modern machines how far you can really get. But just in case, we can basically combine a little bit of the best of both worlds between the localized basis sets and then these spline basis sets. Is that we have a we have a particular ansatz over here called hybrid representation, and it's kind of like a muffin tin setup where you have, like, you basically partition the orbital space, or you partition the real space grid into an area near an atom where the density is going to be changing. This is where this area is what drives up the overall K-space cost, or the plane wave cost over here. And then you have this, like, interstitial region. And so what you do is you kind of do just a localized spherical harmonic spline, radial spline kind of ansatz for the area inside the muffin tin. You use a standard rectilinear grid for the interstitial region, and then you have, like, a nice little mixing region to continuously move between this and this. And I don't know if we have GPU support for this, but if you are running on CPUs, the memory reduction by doing this, and not just memory reduction, but also, like, variance reduction, just because you have a higher resolution representation of this, is pretty sizable. Like, you could easily knock down the cost of storing this spline wave function by about 4 to 8 without any major loss in accuracy. So anyways, if you are interested in this, or if you are hitting up against a hard wall with memory limits, I suggest looking at the hybrid rep tag in the QMCPACK manual and checking out this paper. So this is something that does get used quite a bit in the field. All right. So then we're back to Bloch's theorem. So I've already kind of explained like how do we represent these grids, or how do we represent these orbitals? But it's a single Slater-Jastrow wave function, so we do have to like build up all these orbitals ostensibly for a supercell. So what we kind of do is we try to keep the DFT calculations in the primitive cell as much as possible. And, basically by using suitably chosen K-grids, we unfold this into the supercell we're trying to run. So like, let's say that I'm trying to do a 2x2 supercell in QMC, like I'm not going to run these orbitals in, I'm not going to run the DFT in that supercell. It's just memory intensive, and yeah, it's just wasteful. So so this is kind of what we typically do. This is what's going to be done in the lab. Nexus is smart enough to do this pretty seamlessly, and this particular workflow is also something you could pretty much do by hand based on what QMCPACK already supports. But I was kind of already talking about twist averaging, and when we do supercell extrapolations, we're not just, this is overly simplistic. Like we're not just doing a limited K-point calculation and unfolding it, because actually this would imply that this guy is periodic in this 2x2 cell over here. But usually what we want to do is like, I want to do a 2x2 supercell, and I also want to make sure it's twist averaged. And this case, of course, is this is a particular realization of Bloch's theorem, but this is more in line with what we do on a day-to-day basis, where we'll converge the SCF density, we'll do an NCF calculation at all these different K points, and then we will basically unfold the wave function into a suitable number of single particle orbitals to be used in the supercell. But those supercell orbitals are also going to have twists associated with them, so that just by doing this little Nexus workflow over here, we can basically spin up, a twist averaged supercell calculation. And it's nice. It's pretty screamingly fast when you do it this way. All right. So basically, the general idea for, like, what do you need to look out for when you do solid calculations is that, like, number one, you have to converge. I mean, once the DFTs converge, you have to converge the twist grid. That is always going to be worth your effort. So just do it. And then when possible, I like exploiting symmetry over here. I mean, like, we already have to do this twist grid, but if I can cut down the number of simulations from 25 to 6, that's a win. And I also save on the equilibration time and all the overhead of like spinning up a QMC calculation. And then, it's probably a good idea to like plan ahead for what observables and estimators you want. If you're going to be going through all this effort of like twist averaging, it'd be nice to have a density. You should check to make sure your densities are converged to the extent you want them to, both with regards to finite size errors and, of course, the statistical errors. If you have a low variance wave function, you can be fooled into thinking that like a short run is sufficient for the energy, but the other estimators are going to have issues with them. So, another thing, I guess it depends on like this is more of a research exercise of good judgment, but like you need to know when you need to know when good is good enough. So like, in the lab, tacitly, we're kind of going for 1 millihartree per atom. That's a nice place to go. But like, you do have diminishing returns, and like, there's no real point to resolving a K-point grid and doing all this work to like a microhartree if like, that's overkill. So whenever you're developing your plan for a solid state calculation, you really need to articulate what you need and what's the least you can get away with to guarantee that. And usually this can be done in like a smaller cell. And then, how are you going to quantify, how are you going to mitigate finite size effects in your system? We're going to run you through a K-point convergence example. That's one way to quantify the single particle finite size effects. You know, you should also think about doing like, at least one other supercell size just to check if you need the accuracy to like, well, whatever your accuracy is. I mean, you could also just hold your nose and do KZK or something and just hope that's good enough. Many applications it might be, but you do need to be aware that this is a pretty big deal that can kind of trash things sometimes. And then, like I said, when in doubt, just go to bigger supercell. Then, of course, we are a pretty active community with a very active Slack. We have our main Slack over here, but we also have our workshop. So if you have any questions about this, definitely reach out. All right. So this lab that you will be doing, if you care to, is steps 1 through 3 are going to be a very standard QMC, DFT QMC workflow that you've already done in this lab. Is you generate the SCF density, and then that whole thing about Bloch's theorem where we're unfolding stuff is that we use this converged SCF density to do that K-point calculation for future unfolds. We optimize the J1 and 2, and basically that is what forms the basis of this calculation. Now, once you have your J1 and J2 set up, then you're going to go through a series of calculations with VMC and DMC for several different twist grids. And so, incidentally, like, you will notice that like these are actually the twist grids over the irreducible Brouillard zone. These are the symmetry aware twist grids. The README on the GitHub will walk you through what the output files mean, and then kind of like what the code is specifically doing when you're doing one of these twist grid calculations. And then, once you're done with that, you will twist average the results in each of these twist grid calculations, and then that will give you enough to determine whether or not you're converged or not. So as a spoiler alert, the lab that you did will go, this is at 1 twist, that is at a 2x2, 3x3, so 27. I also ran on a bigger machine, 4x4 and 6x6. So we do know what converged is. But, I think it's important to go through the exercise and see, just see how the workflow works, just get a feel for it, and then do the analysis yourself. So, and that is everything I got. Thank you for listening to this tutorial about solids. And if there are any questions, I will gladly take them and hopefully answer them.
Thanks very much, Ray. Yeah, if you leave the slides up, that would be helpful. The talk is open to questions. I have actually a comment on your slide, I think it's 24 on the splines.
Yes.
Ray, and then a question about twists.
Yeah.
So first, just a comment. So as Ray explained, yes, right, B-splines are the fastest, really most efficient way to run solids, as there's only the 64 grid points that need to be touched upon to evaluate one orbital. The trade-off is, of course, as Ray explains, you use a lot of memory for large systems and low symmetry systems. What I wanted to mention is that QMCPACK also has an implementation of periodic Gaussians or periodic LCAO, which currently talks to PySCF. It could straightforwardly talk to other codes. So that's a different trade-off. So that's a trade-off where it has a basis set that's quite low memory, very low memory by comparison, but then you have to choose the basis set. And essentially, by definition, it's going to be slower and have a worse scaling with the basis set size than the splines. But of course, it's always going to fit in memory. So that's a trade-off that some people like to make. And also, you don't have to pay for vacuum, for example, which you do with these grids. So there are some other options there. And as Ray said at the end, just ask on one of the various support channels if you're wondering about what might be a good route or you run into issues. Now, my question is about twists, Ray. And do you have any sort of guidance on where and when they are particularly important and where more might be needed? And to see the answer, I'll make a comment that, for example, I've seen molecular crystal calculations, which are presumably insulators in high impact journals, run with just one or no twists, essentially a gamma point.
Yeah.
Whereas you mentioned grand canonical, which I think was first done for metals, and I think a lot of twists were needed in that case.
Yeah. So this pretty much gets to like a pretty deep solid state physics, but as a general rule, metallic systems are you need a lot more K points to handle the finite size effects, both in QMC. So you need a very dense K point grid in QMC, but you also need it in DFT as well. And like the consequence of, I mean, the reason for that is kind of like is shown in this like 2D electron gas kind of example, is that in metals, like your occupations go in the thermodynamic limit go all the way up to this Fermi surface. And there are finite excitations that will just like, everything around this kind of determines the physics of a metal, of like at least a standard Fermi liquid metal. And to a lesser extent, like, semiconductors and semi-metallic systems as well, there's a lot of physics baked into like what's happening right around here. So for things like molecular crystals and strong insulators, though, it's like, I mean, the thing's gonna have a Fermi surface, but like the excitations and like it's almost like the window of K space that you need to describe the system is just not nearly as big. Like you might have your Fermi surface, but like, you're gonna have to pop way up somewhere here to be able to like go to the next excited state. So it's like, so oftentimes in those situations, you can get away with either like one, like even at like a gamma point calculation, which is, for non-solid state practitioners, is the K point corresponding to 0, 0, 0. Um, but ultimately the way to tell is to check it. And if you do these calculations enough, you start getting an intuition, like you can start looking at the DFT and seeing like, wow, that thing was done after like 2 K points. The QMC might not be the exact same, but that'll set the order of magnitude for it. And so I guess the other things to look out for would be like, layered materials or like things with like unusual, like, or other systems with very unusual Fermi surfaces where you think that physics has any bearing on the physics you're looking at. Probably says you're going to have to resolve that. So that's another situation where the twist grids and even the corresponding DFT grids are probably going to have to be larger. So
Thanks, Ray. I think that really captures it. So I don't see any questions yet, either in the Slack or in the Zoom chat. So we'll give it a few more moments. I would just like to encourage everyone to try running the lab after doing those updates that we described, as there's quite a few moving pieces here, but I think it will be a lot clearer after going through the exercise as Nexus really automates most of it. So I think it'll be a lot clearer after running